Let's now consider the case where we deal with a solution in which the delta G of mixing has some sort of maximum in it. As we could see here, if we're near a maximum, there exist possibilities in which the system could lower a free energy by going into different compositions, or phase separating to different compositions, right? And so here, if the system starts out initially here, it could phase separate such that it forms one phase with composition xa prime or x1 prime and another composition x1 double prime, right? And the compositions would be set in such a way that you could draw a straight line between them, okay? So let me express that in words. If, and I'll call the initial composition, I'll put it in brackets, so like it's the average composition of the entire system. So if xa is near a maximum in delta G mix, then there are two different compositions, or the composition of two different phases, such that a straight line between them would lower delta G mix. Okay? Alright, and so that begs the question, how do we find the equilibrium values of xa prime and xa double prime? Okay? And why exactly is that straight line important? The answers to this question all result from our definitions of the equilibrium criteria. So we could find those values by using the equilibrium criteria. Right? And essentially, what we have to remember is that at equilibrium, the chemical potential of species A in phase prime, which is a function of xa, that has to be exactly equal to the chemical potential of species A in phase double prime. And the same thing is true for chemical potential B. And I'm still writing it as a function of xa, right? Since we're just dealing with a binary system. Okay? Whoop. Alright, so that's the equilibrium criteria. Right? And in order to institute this criteria, we're going to use what's known as the common tangent construction. So, can identify this condition using the common tangent construction. Okay? Alright, and so what that means is that if we think about delta G mix, we've written in many different ways, but another way that we could write it is actually in terms of the chemical potentials, right? Such that delta G mix would just be equal to the sum of Na times some sort of change in chemical potential A plus Nb times some sort of change in chemical potential B, where these changes in chemical potentials are just the difference between chemical potential A minus its standard state value, and the same for chemical potential B. Right? This is, if you think about it, this is one way that you could write delta G of mixing. Alright, if we divide delta G, a mix, by the total number of molecules in the system, that's the molar delta G mix. And so what we get is that we have XA now times mu A plus 1 minus XA delta mu B, where XA is just NA divided by N. Okay. Alright, now that we have this expression, we could rearrange it like this and distribute across the XA term and then factor it out. So we have mu A, mu B, all that times XA plus delta mu B. Okay? And by rearranging it into this form, we see that we just have a linear equation with respect to XA, such that this is the slope and this would be the intercept. Okay? So I'm going to call this equation 1. Right, and so we have this straight line. And if we go back to this relationship where we're plotting our delta G mixing, this is really the molar, we see that we now have this straight line where the slope corresponds to delta mu A minus delta mu B, and the intercept is that delta mu B. Okay? Alright, and so if we write this out, I'm going to write out the steps. By looking at that plot, what you could do is if you draw delta G mix curve that is tangent, so it touches the line but doesn't cross through it, so it's tangent at 2 points, XA double prime, you can use equation 1 to get delta mu A and delta mu B. Okay? And so in other words, by kind of sketching out this line such that it only touches this delta G curve in 2 spots, once you draw that line, if you get the intercept of that line, that'll give you the delta mu B, and then here this will get you the difference between delta mu A and delta mu B, and then using your intercept you could then solve for delta mu A. Okay? Alright, and so the utility of this is that since tangent line works for XA prime and XA double prime, that means that the delta mu B that you calculate which is a function of XA prime, that's also equal to the delta mu B that you get for XA double prime. And the same for delta mu A XA prime is equal to the delta mu A XA double prime. Okay? And essentially, therefore, common line identifies XA as the equilibrium mole fractions. Okay? All right, and so in other words, from the plot, by finding out where this line is tangent to the curve, that allows us to get XA prime and XA double prime. Furthermore, it also allows you to get the chemical potential values. And what you could do there is you could cross-check your chemical potential values by just plugging in, whatever model you use to get the chemical potentials. That model will be a function of XA, and so you could also just solve those equations in order to get XA and XA prime. Okay. All right. So a couple of notes that I'm going to put here. For regular solution theory equation, if we plotted this curve out for the regular solution theory, it wouldn't be diagonal like this. It would actually be kind of horizontal. And your XA prime and XA double prime would actually correspond to local minimums in the curve. Okay? So XA prime and XA double prime correspond to delta G mixing minimums. Okay? But in general, that's not true, right? So this is not true for other delta G mixing models, right? And so if we look at more complicated models, you can't really just calculate the minimums of this delta G mixing curve. You actually need to, find where the chemical potentials are equal to one another. Okay? And so in general, to calculate the binodal, really the strategy you want to do is you want to vary your mole fraction. So just come up with a range of mole fractions that you want to look at. Then you want to calculate delta G mix using whatever model you're using, so whether it's a regular solution theory or something more complicated. And then if delta G mix has a maximum, so if there is something that's concave down, that tells you phase separation can occur. And so what you got to do at that point is you got to calculate your XA prime and XA double prime using the common tangent rule. Right? Or alternatively, you could directly solve mu I equilibrium criteria. Right, so what you would do is you would use your equations for the different chemical potentials to then just calculate. You would relate those equations, so both at the same time, and then solve for the mole fraction. Okay? All right, using these strategies, you could then develop a curve that looks like this, where here we have our binodal curve. And we did this for a system in which we used a regular solution theory, and the chi parameter was equal to this constant of 5,000 divided by RT. And that's just to get the units of the delta G mixing into like joules per mole. All right. But as you can see here, when we have this curve, we have this binodal curve, so that tells us if our XA is equal to 0.5 and we're below a temperature of 300, then our system would phase separate into A rich and A poor phases.